somewhere out in the deep dark of the galaxy, a star is dying. And it is the most beautiful thing you will ever see. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. Picture yourself floating far above the Milky Way, looking down at the slow, quiet spin of 100 billion stars. Most of them are tiny points of light, steady and calm. But here and there, scattered across the spiral arms like glowing lanterns, you can see something different. Soft rings of color, pale shells of blue and green and red, drifting outward in perfect silence. Each one is a star in its final hours, breathing out its last great breath into the dark. These are planetary nebulae. The name is a little misleading, and it has been from the very start. They have nothing to do with planets. When astronomers first spotted them through early telescopes hundreds of years ago, the soft, round glow reminded them of the pale disk of a distant planet. The name stuck, even though we now know better. A planetary nebula is not a planet, and it is not a cloud in the way we usually think of clouds. It is something far more extraordinary. A planetary nebula is the glowing shell of gas that a dying star pushes outward into space. When a star like our sun reaches the very end of its life, it does not explode in a violent burst the way massive stars do. Instead, it swells up slowly, then gently releases its outer layers. Those layers drift away in great expanding rings and shells, lit from within by the hot, dense core the star leaves behind. The result is one of the most stunning sights in the known universe. Think about what you are actually looking at when you see one of these objects. That soft, glowing ring of color was once the outer body of a living star. The atoms inside it were forged in the star's core over billions of years. Now they are free, spreading slowly outward, carrying with them the carbon and nitrogen and oxygen that the star spent its whole life building. A planetary nebula is not just beautiful. It is generous. It is a star giving everything it ever made back to the universe. The glowing gas in a planetary nebula is not solid or thick. It is incredibly thin, far thinner than the best vacuum we can create here on Earth. If you could somehow fly a spacecraft straight through one, you might not even notice the gas around you, but seen from a distance, lit by the fierce ultraviolet light pouring out of the dying star at the center, that thin gas blazes with color. It glows. It shimmers. It holds its shape for tens of thousands of years before slowly fading back into the dark. At the heart of every planetary nebula sits what remains of the original star. It is called a white dwarf, a small, incredibly dense object about the size of Earth, but with a mass close to that of the Sun. This white dwarf is extraordinarily hot when it first forms, sometimes reaching temperatures above 100,000 degrees. That fierce heat is what powers the whole glowing display. The white dwarf pours out radiation, and the surrounding gas absorbs that energy and shines. Scientists estimate there are roughly 10,000 planetary nebulae scattered across our galaxy right now. That sounds like a lot, but in a galaxy with hundreds of billions of stars, it is a remarkably small number. That is because a planetary nebula does not last very long. In cosmic terms, most of them fade and dissolve within 20 to 50,000 years. On a human timescale, that sounds enormous. But the universe is nearly 14 billion years old. A planetary nebula is a brief flash of color in an almost endless night. And yet, brief as they are, they matter enormously. Every planetary nebula you see is a delivery system. It carries the raw materials for new stars, new planets, and perhaps new life out into the spaces between the stars. The universe recycles everything. Nothing is ever truly lost. A star dies, and its atoms drift outward, and one day, far in the future, those same atoms may find themselves inside a new sun, or a rocky world, or something we have not yet imagined. Close your eyes for a moment and picture that soft ring of light hanging in the dark. That is where we begin. Not every star in the sky will one day make a planetary nebula. That is the first thing to understand. The universe is full of stars of many different sizes, and only a certain kind will end its life in that soft, glowing cloud of gas and light. The stars that make planetary nebulae are called low to intermediate mass stars. is the technical name, but what it really means is this: they are stars that weigh somewhere between about half the mass of our sun and roughly 8 times the mass of our sun. Stars lighter than that tend to burn very slowly and quietly, and they fade out in a different way. Stars heavier than 8 solar masses live fast and die violently in massive explosions called supernovae. But the stars in the middle range, the ones like our own sun, those are the ones that end their lives by gently breathing out their outer layers into space. Our sun falls right in the middle of this range. It is a perfectly ordinary star. It is not especially large. It is not especially bright. Astronomers sometimes call it a yellow dwarf, which is a small, stable, middle-aged star that burns hydrogen in its core. And one day, billions of years from now, our sun will go through the same process that creates a planetary nebula. That is not a sad thought. It is simply the way the universe works. Stars like our sun are extraordinarily common. Scientists estimate that somewhere between 70 and 80% of all stars in the Milky Way fall into this low to intermediate mass category. That means the vast majority of stars you see on a clear night are the kind that will eventually, at the end of their lives, produce one of these glowing shells of gas. The night sky is full of future planetary nebulae, waiting quietly for their time. Now, these stars are not young when they make a planetary nebula. They are very, very old. A star like our sun burns for roughly 10 billion years before it begins the process that leads to a planetary nebula. Our sun is about 4.5 billion years old right now, which means it is roughly halfway through its life. The stars that are currently producing planetary nebulae in our galaxy have been burning for billions of years already. They have spent most of their existence as steady, stable, hydrogen-burning stars, just like our sun is today. To put that in human terms, imagine a person who lives to be 100 years old. The planetary nebula phase of a star's life is like the very last few months of that person's life. Everything that came before, all those billions of years of steady burning, was the long, quiet middle. The planetary nebula is the final, luminous exhale. The mass of a star matters enormously. A star that that is more massive than our sun burns hotter and faster. It uses up its fuel more quickly. A star with twice the mass of our sun might only live for 2 or 3 billion years before it begins to age. A star with half the mass of our sun burns so slowly and gently that it could live for tens of billions of years, longer than the current age of the universe itself. In fact, the very smallest stars in this range have not yet had time to finish their lives. The universe is not old enough yet for them to have reached their end. This means that the planetary nebulae we see today were mostly made by stars that formed long ago. In the early and middle chapters of our galaxy's history, they are, in a sense, messages from the past. The light and gas we see glowing in those shells was once locked inside a star that burned when our solar system was young, or perhaps even before it existed at all. There is something quietly wonderful about that. The atoms drifting outward in a planetary nebula right now may have been sitting inside a star for 5 or 6 or 7 billion years. They were held there, fused and transformed, and now they are free. They are moving outward through space at speeds of 10 to 30 kilometers per second, which is fast enough to cross the entire continental United States in a fraction of a second. And yet, compared to the vast distances of space, that movement is slow and gentle, like smoke rising on a still evening. These are the stars that make planetary nebulae. Ordinary stars. Stars like our sun. Stars that have lived long, steady lives and are now, at the very end, giving something back to the universe that made them. To understand how a planetary nebula is born, you have to go back a very long way. You have to go back to the beginning of the star itself. Every star begins the same way. Somewhere in a galaxy, there is a vast cloud of gas and dust floating in the dark. These clouds are called nebulae too, though a different kind. They are cold and thin and spread across enormous distances. A single cloud like this can stretch for hundreds of light years. For a long time, nothing happens. The cloud just drifts. Then something disturbs it. Maybe a nearby star explodes. Maybe 2 clouds drift close enough to nudge each other. Whatever the cause, a small part of the cloud begins to pull inward. Gravity does what gravity always does. It draws things together. Slowly, over millions of years, a pocket of gas and dust grows denser and denser. It begins to spin. It begins to heat up. At the center of this spinning, collapsing cloud, the pressure becomes enormous. The temperature rises into the millions of degrees. And then, at a certain threshold, something remarkable happens. Hydrogen atoms are squeezed so tightly together that they fuse. They merge into helium. And in that merging, they release energy. Light, heat, radiation. A star is born. For a star like our sun, this moment of first light happens after about 50 million years of collapse. That is a long time by human standards. But in the life of a star, it is just the opening breath. Once a star like this settles into its rhythm, it enters a phase called the main sequence. This is the long, quiet middle of a star's life. The star burns hydrogen in its core, and the energy that burning produces pushes outward against the pull of gravity. These two forces balance each other almost perfectly. The star holds its shape. It holds its size. It glows steadily, year after year, century after century, millennium after millennium. For a star like our sun, this steady burning phase lasts about 10 billion years. Our sun is about halfway through that span right now. It has been burning for roughly 4.5 billion years, and it has about 5 billion more to go before things begin to change. That is a span of time so large, it is almost impossible to hold in your mind. The entire history of life on Earth fits inside just the second half of our sun's main sequence life. During all those billions of years, the star is not simply sitting still. It is working. It is fusing hydrogen into helium in its core, and that helium slowly builds up like ash settling at the bottom of a fire. The core grows heavier and denser with each passing age. The hydrogen in the very center begins to run out. The star does not notice this for a long time. The burning simply moves outward into a shell around the core, and the star keeps going. This is the quiet part of the story, the long, uneventful middle, and it is easy to overlook because nothing dramatic happens. But this is where the real work is done. This is where the star builds up the material that will one day become a planetary every atom of carbon, every atom of nitrogen, every atom of oxygen that will one day drift outward in a glowing shell of gas was forged during this long, steady burning. The star is, without knowing it, preparing a gift for the universe. Stars that are more massive than our sun burn faster and hotter. They race through their hydrogen in just a few 100 million years. But those massive stars do not make planetary nebulae. They end in a different kind of explosion entirely. The stars that make planetary nebulae are the calm ones, the patient ones, the stars between about half the mass of our sun and roughly 8 times the mass of our sun. These stars burn slowly and steadily for billions of years before anything changes. There is something deeply calming about that image. A star holding itself together through nothing but the balance of two forces, burning quietly in the dark for longer than the earth has existed. No drama, no sudden change, just a steady, patient glow year after year for billions of years. And all the while, deep in its core, the helium is building up. The hydrogen is slowly running thin. The balance that has held for so long is beginning, very gradually, to shift. The star does not know what is coming, but the universe does. And the next chapter, when it finally arrives, will be one of the most beautiful transformations in all of nature. That shift begins deep inside the star, in a place no light can reach. For billions of years, the star has been fusing hydrogen into helium in its core. That process, called nuclear fusion, is simply the joining of small atoms to make larger ones. It releases an enormous amount of energy. That energy pushes outward. Gravity pulls inward. The two forces stay matched, and the star holds its shape. But hydrogen does not last forever. Slowly, over billions of years, the core fills up with helium ash. The hydrogen fuel thins out. And when the core can no longer fuse hydrogen at the rate it once did, that careful balance begins to tip. The core starts to shrink. Gravity wins just a little. The core squeezes tighter and tighter, and as it does, it heats up. This is simply what happens when gas is compressed. It grows hotter. The core temperature climbs. And eventually, something new begins. The helium itself starts to fuse. Helium fusion is a different kind of fire. It runs hotter than hydrogen fusion, and when it ignites, it does not do so gently. Scientists call the moment helium fusion begins in a low-mass star the helium flash. It is a sudden, powerful burst of energy deep inside the core. The star does not explode. Nothing visible happens on the outside, not right away. But inside, in the space of just a few minutes, the helium core releases more energy than the sun puts out in hundreds of millions of years. It is one of the most powerful events in a star's life, and it happens in complete silence, hidden deep beneath layers of gas. What comes out of helium fusion is carbon. Two helium atoms fuse to make beryllium, and then a third helium atom joins to make carbon. This process is called the triple alpha process because helium nuclei are sometimes called alpha particles. The result is a core that slowly fills with carbon and oxygen, the same elements that form the backbone of life on Earth. Think about that for a moment. The carbon in every living thing, in every tree, in every human body, was forged inside a star through this exact process, not a different process. This one, the same quiet nuclear reaction happening inside a dying star billions of years ago, made the carbon that eventually became part of you. And it does not stop there. As the star fuses helium in its core, it also begins fusing hydrogen in a shell just outside the core. This shell burning adds more helium to the core from above, feeding the fire. The star is now running two separate fusion reactions at once, layered like the rings of an onion. The core burns helium. The shell above it burns hydrogen. The energy from both pushes outward through the star's outer layers. Those outer layers begin to respond. They expand. The star grows larger, slowly at first, then more dramatically. The surface cools as it spreads out, and the star turns redder. This is the beginning of the red giant phase, the long, swelling transformation that will eventually lead to the star letting go of its outer layers entirely. The elements building up inside the star at this stage are not exotic or rare. They are familiar. Carbon, oxygen, nitrogen, which forms in the hydrogen-burning shell. These are the same elements that fill Earth's atmosphere atmosphere, that dissolve in the ocean, that build proteins and DNA. The universe makes them inside ordinary stars, stars just like the sun, through processes that have been running for billions of years across every corner of the galaxy. There is something quietly remarkable about that. The atoms in the air you breathe right now were not always here. They were made somewhere else, inside a star that lived and aged and eventually let go. They drifted through space. They gathered into clouds. Those clouds collapsed into new stars and planets. And here they are now, surrounding you, filling your lungs, part of the world you live in. The star does not yet know it will share these gifts. It is still in the early stages of change, its core heating, its layers shifting, its outer envelope beginning to stir. The helium is burning. The carbon is building. The star is growing slowly larger and cooler on the outside, while growing hotter and denser on the inside. Two different things are happening at once, pulling in two different directions. And that tension between the swelling outer layers and the shrinking, heating core is what will drive everything that comes next. The star is beginning, very slowly, to let go. That tension lives inside the star like two hands pressing against each other. One pushes outward, one pulls inward, and the star holds its shape only because these two forces stay in balance. The force pulling inward is gravity. It is always there, always working, always trying to collapse the star down to nothing. Gravity never rests. It has been squeezing this star since the very beginning, since the first cloud of gas pulled itself together billions of years ago. Every atom in the star feels that pull, tugging toward the center, pressing inward from all directions at once. The force pushing outward is pressure. Deep in the core, nuclear reactions release enormous amounts of energy. That energy pushes back against gravity. It holds the star open, like a breath held inside a balloon. As long as the core keeps burning, the star keeps its shape. The two forces match each other almost perfectly, and the star floats in a kind of steady stillness for millions or billions of years. But now, the balance is shifting. The core has been burning hydrogen for a very long time. Hydrogen is the lightest element, and it burns easily. When hydrogen of all that burning. Eventually, the hydrogen in the core runs out. The core goes quiet. And when the core goes quiet, gravity wins a little more ground. The core begins to shrink. As it shrinks, it heats up. This is a basic rule of physics. Squeeze something and it gets hotter. The core grows denser and hotter at the same time, pressing inward on itself with tremendous force. Meanwhile, the heat pouring out of that shrinking core pushes into the layers above it, like warmth rising from a fire. Those outer layers begin to expand. They swell outward slowly, cooling as they spread. The star grows larger on the outside while growing smaller and hotter on the inside. This is how a red giant is born. The outer layers of the star can expand to enormous sizes during this phase. A star like the Sun will eventually grow large enough to swallow the inner planets of its solar system. The surface temperature drops as the gas spreads out, which is why the star turns red. Red light comes from cooler surfaces. The star is not dying yet. It is changing shape, redistributing its energy, finding a new kind of balance. Inside the core, something new begins. The helium that built up over billions of years is now under so much pressure and heat that it starts to fuse. Helium burning is different from hydrogen burning. It requires far higher temperatures to get started, but once it begins, it releases energy in a powerful burst. Scientists call this the helium flash, a sudden ignition deep inside the core that releases as much energy in a few seconds as the sun puts out in millions of years. The star does not explode. The energy is absorbed by the dense layers surrounding the core, but the star is changed. A new phase of burning has begun. Radiation pressure also plays a quiet role in all of this. Radiation pressure is the gentle push that light itself exerts on matter. Deep inside a star, photons, which are tiny packets of light, bounce outward through the dense gas. Each bounce pushes the gas slightly outward. In a normal star, this force is small compared to gravity. But as the star ages and its luminosity increases, the radiation pressure grows stronger. In the outer layers of a red giant, this pressure begins to lift gas away from the star, sending thin streams streams of material drifting out into space. The star is not exploding. It is exhaling. Magnetic fields thread through the star as well. Stars rotate, and that rotation, combined with the churning of hot gas rising and falling inside the star, generates magnetic fields. These fields twist and loop through the outer layers. They can shape the way gas flows. They can create regions where material escapes more easily. Scientists believe that magnetic fields may help explain why some planetary nebulae take on strange and beautiful shapes later in their lives, guiding the outflowing gas into spirals, rings, and jets. All of these forces, gravity, pressure, radiation, magnetic fields, are working together and against each other at the same time. None of them acts alone. Each one shapes what the others can do. The star is not simply falling apart. It is being sculpted slowly and precisely by the same invisible forces that have governed it since the very beginning. The giant is still growing. The core is still heating, and the star is still very gently beginning to let go. And now the letting go truly begins. When a red giant starts to shed its outer layers, the process is slow beyond imagining. The star does not burst. It does not crack open. It simply breathes outward year after year, century after century, releasing a thin and steady wind of gas into the dark around it. This wind is called a stellar wind, and in the early stages, it is surprisingly gentle. The gas drifts away from the star at speeds of roughly 5 to 10 miles per second. That sounds fast, but compared to what comes later, it is barely a whisper. To understand how much material a star eventually releases, you need a number that is hard to hold in your mind. A star like our sun will shed somewhere between 40 and 60% of its total mass before it is finished. Not a small flicker of itself, nearly half. All of that material, all of that gas and dust will drift outward into space and become the glowing cloud we call a planetary nebula. Our sun contains more than 300,000 times the mass of Earth. Losing half of that means releasing an almost incomprehensible amount of material into the universe. Here is a way to feel that scale. Imagine imagine filling the entire Pacific Ocean, not once, not 100 times, but billions upon billions of times over. The total mass shed by a sun-like star during this process dwarfs anything we can hold in our hands or see with our eyes. And yet, it happens quietly, slowly, over tens of thousands of years. The outer layers do not all leave at once. The shedding happens in stages. In the early phase, the stellar wind is slow and thin, building up a large, loose shell of gas around the star. This shell can grow enormous. Some of these early shells stretch for a light year or more across, and a light year is nearly 6 trillion miles. If you could drive a car at highway speed without stopping, it would take you more than 6 million years to cross a single light year. These shells are so large and so thin that they are nearly invisible, even to powerful telescopes. They are there, surrounding the star like a vast and silent fog, waiting. Then something changes. As the star continues to evolve, the stellar wind speeds up dramatically. In the later stages, the wind can reach speeds of hundreds of miles per second. This fast wind slams into the slow, thin shell that was released earlier. It compresses it. It pushes it outward. It sculpts it. Scientists call this the interacting winds model, and it helps explain why planetary nebulae develop their sharp, glowing edges. The fast wind acts like a snowplow, gathering the older gas into bright, defined shells and rings. That is why so many nebulae look so crisp and clear, even from thousands of light years away. The temperatures inside these outflowing layers are worth pausing on. The gas leaving the star's surface is not especially hot by stellar standards, perhaps a few thousand degrees. But as the nebula forms and the hot core of the star is exposed, that changes. The white dwarf at the center, which we will visit soon, can reach temperatures of 100,000 degrees or more. That extreme heat sends out powerful ultraviolet light, the kind of light that carries enormous energy. This light floods into the surrounding gas and heats it, excites it, makes it glow. The nebula lights up from the inside out, and the size of the final nebula, the fully formed glowing cloud, is staggering. are larger. The Helix Nebula, one of the closest to Earth, stretches roughly 2.5 light years from edge to edge. If you placed it where our sun sits, its outer edge would reach well past our nearest neighboring star system, Alpha Centauri. The entire space between us and our closest stellar neighbor would be filled with glowing gas. All of this, the slow wind, the fast wind, the vast expanding shell, the heating and the glowing, unfolds over a span of roughly 10,000 to 30,000 years. On a human timescale, that is an eternity. On the timescale of the universe, it is a single breath. A star that burned for billions of years releases its outer self in what amounts to a brief, quiet moment. And in that moment, it creates something that glows across the darkness of space like a lantern left burning in an empty field. The outer layers are gone now. What remains at the center is small, dense, and extraordinarily hot. And it is just beginning its own remarkable story. At the heart of every planetary nebula, something extraordinary sits waiting. It is the white dwarf. This is the dense, hot core left behind after a star sheds its outer layers into space. It is not a new object, exactly. It is the old heart of the star, exposed at last, stripped of everything that once surrounded it. A white dwarf is almost unimaginably small for something that was once a star. Our sun, when its time comes, will leave behind a white dwarf roughly the size of Earth. Think about that for a moment. A star that currently spans about 865,000 miles across will compress down to something closer to 8,000 miles wide. The same amount of matter packed into a space incomparably smaller. A single teaspoon of white dwarf material would weigh several tons if you could somehow bring it to Earth and set it on a scale. That compression comes from gravity. When the outer layers of the star drift away, nothing is left to push back against the pull of the star's own weight. The core collapses inward, but it does not collapse all the way to nothing. A force called electron degeneracy pressure holds it steady. The electrons inside the dense matter press against each other and refuse to be squeezed any further. The collapse stops. What remains is solid, dense, and stable in a way that that feels almost stubborn. If you could float above a white dwarf and look down at its surface, you would not see fire or flame the way we picture the sun. The surface of a white dwarf is not burning in the traditional sense. There is no nuclear fusion happening there anymore. The heat you would feel radiating outward is leftover heat, the stored energy of billions of years of stellar life slowly leaking into space. The surface glows because it is hot, not because it is actively burning. It is more like a coal pulled from a fire than a flame itself, and it glows intensely. Newly formed white dwarfs at the center of planetary nebulae can reach surface temperatures of around 100,000 degrees Celsius, or even hotter. Some push past 200,000 degrees. For comparison, the surface of our sun sits at roughly 5,500 degrees Celsius. The white dwarf is many times hotter, even though it is far smaller and producing no new energy of its own. That extreme heat is what makes it so powerful. It floods the surrounding gas cloud with ultraviolet light. The high-energy radiation that causes the nebula's gases to glow in those brilliant colors we see from Earth. The color of the white dwarf itself, if you could see it clearly, would be a fierce blue-white, not the warm yellow-orange of our sun, not the deep red of a cooler star. A sharp, piercing, almost clinical blue-white, like the hottest part of a flame held very close. Over millions and billions of years, the white dwarf will cool. That blue-white will slowly fade toward white, then yellow-white, then a pale yellow. Eventually, far in the future, it may cool to something dimmer. Scientists call this theoretical end state a black dwarf, a cold, dark, inert remnant. But the universe is not yet old enough for any black dwarfs to exist. Every white dwarf ever formed is still glowing somewhere. The surface of a white dwarf is also remarkably smooth compared to what we think of as a star's surface. Our sun churns and bubbles with convection, with plasma rising and falling in massive loops. A white dwarf, by contrast, has a surface that is relatively calm. The intense gravity, roughly 100,000 times stronger than Earth's gravity at the surface, flattens everything. Any mountain on a white dwarf would be measured in millimeters. The gravity would not allow anything taller to stand. That same crushing gravity means the atmosphere of a white dwarf is extraordinarily thin and stratified. Heavier elements sink quickly. Lighter elements like hydrogen and helium float to the top. Some white dwarfs show a thin layer of hydrogen at their surface. Others show helium. Astronomers can read these layers like a label, learning something about the star's history from what floats at the very top. Floating above this small, fierce, blue-white object, surrounded by the slowly expanding glow of the nebula it created, you would be looking at one of the quietest and most enduring things in the universe. The chaos of the star's final expansion is over. The nebula drifts outward in slow silence, and the white dwarf simply glows, steady and patient, releasing the last of its ancient warmth into the cold dark of space. That glow surrounding the white dwarf is not simple white light. It is something far richer. The expanding shell of gas that the dying star released catches the fierce ultraviolet radiation pouring from the white dwarf's surface, and it answers back in color. Each color you see in a planetary nebula is a message. Each one tells you exactly which element is glowing. This process is called emission. When ultraviolet light from the white dwarf strikes a gas atom in the surrounding shell, it knocks electrons loose from that atom. The electrons absorb energy and jump to a higher state. Then they fall back down, releasing that energy as light. The color of that light depends entirely on which element the electron belongs to. Hydrogen glows red. Oxygen glows blue-green. Nitrogen glows deep red and orange. Sulfur adds its own warm tones. Every element has its own signature, like a fingerprint written in light. Astronomers use a tool called a spectrograph to read these signatures. A spectrograph splits incoming light into its separate colors. The way a prism spreads sunlight into a rainbow. When astronomers point a spectrograph at a planetary nebula, they see a pattern of bright lines. Each line marks a specific element. By reading those lines, scientists can tell you exactly what the nebula is made of, how fast the gas is moving, and even how hot it is. All of that information is hidden inside the color. green glow you see in so many famous nebula photographs comes mostly from oxygen, not the oxygen we breathe, but a form of it that has lost 2 electrons, called doubly ionized oxygen. Scientists give it the shorthand name OIII. This particular form of oxygen glows at a wavelength that human eyes find vivid and striking. It is the color that gives the ring nebula its inner glow and lights up the center of the cat's eye nebula like a pale turquoise flame. Red and pink tones in a nebula usually come from hydrogen. Hydrogen is the most common element in the universe, and it is plentiful in the outer shells of these dying stars. The specific red glow from hydrogen is called hydrogen alpha emission. It sits at the red end of the visible spectrum. When you see a nebula with deep crimson edges fading into blue-green at its core, you are watching hydrogen and oxygen painting a picture together, each responding to the same source of ultraviolet light in its own way. Some of the colors in a planetary nebula cannot be seen by human eyes at all. Ultraviolet light and X-ray light pour from the white dwarf at the center, and the gas shell absorbs and re-emits some of this energy at wavelengths beyond what our eyes can detect. Space telescopes like the Hubble Space Telescope and the Chandra X-ray Observatory capture these invisible wavelengths and translate them into colors we can see. The vivid, layered images of nebulae you may have seen are often composite images built from several different wavelengths of light layered together. The colors are real in the sense that they represent real emission from real elements. They are simply translated into the visible range so we can appreciate what is actually there. The temperature of the white dwarf controls how brightly the nebula glows. A hotter white dwarf pumps out more ultraviolet radiation. More ultraviolet radiation means more ionization, which means more electrons jumping and falling and releasing light. The very hottest white dwarfs, with surface temperatures above 100,000 degrees Celsius, can ionize the gas shell so completely that it blazes with color across a wide range of wavelengths. Cooler white dwarfs produce a softer, quieter glow. As the nebula expands and the gas spreads thinner over time, the glow slowly fades. The atoms drift fewer collisions happen. The light grows dimmer. The colors do not disappear all at once. They thin gradually, like watercolors diluted with more and more water, until eventually the nebula becomes too faint to see. What remains is the white dwarf, still glowing quietly, and the elements it scattered, now drifting free through interstellar space. Every color in a planetary nebula is a record of something real. The red edge is hydrogen that once burned inside a star for billions of years. The blue-green center is oxygen forged in nuclear reactions deep in that star's core. These are not decorations. They are the actual substance of a star, set free and lit up for a brief, brilliant moment before dissolving into the dark. The universe is writing its own history in light, and for a few thousand years, a planetary nebula lets us read it. The colors fade, the light thins, but before a planetary nebula disappears completely, it leaves behind something worth looking at very carefully: its shape. And the shapes these nebulae take are some of the most varied and surprising forms in all of nature. Most people, when they first hear the word nebula, picture a soft, round cloud, a gentle sphere of glowing gas, like a soap bubble drifting through space. And some planetary nebulae do look exactly like that. Scientists call these spherical nebulae, and they form when a star sheds its outer layers evenly in all directions, like a slow, steady breath released into the dark. The gas spreads outward in a smooth, expanding shell. From any angle, it looks the same: round, soft, complete. But most planetary nebulae are not round at all. The most common shape is something called bipolar. That word simply means two poles, and it describes a nebula that pushes outward from two opposite sides, forming a shape that looks like an hourglass or a pair of wings. The gas flows out from the top and bottom of the dying star, but not so much from the sides. The result is a pinched, elegant form. The Twin Jet Nebula, also known as M29, is one of the most striking examples. Its two glowing lobes stretch outward like the wings of a butterfly frozen in light. The structure is so symmetrical, it almost looks designed. These bipolar shapes form because of the way a star spins. Stars As a star ages and begins to shed its outer layers, that rotation matters. The gas near the star's equator, the widest middle part, tends to be denser. It resists the outward flow. The gas near the poles, the top and bottom, escapes more easily. So the nebula bulges outward at the poles and gets pinched tight at the middle. The spin of the star, carried all the way from its birth, shapes the final form of its death. Some planetary nebulae take even stranger forms. There are elliptical nebulae, which are stretched into oval shapes rather than perfect spheres. There are ring nebulae, where the gas forms a glowing band around the central star, like a smoke ring floating in space. The famous ring nebula in the constellation Lyra looks exactly like that. A soft, greenish-blue oval ring with a faint white star at its center. It sits about 2,600 light-years away, and even a modest telescope can reveal its shape on a clear night. Some nebulae develop multiple shells. As a star pulses and sheds gas in waves over thousands of years, each wave of expelled material forms its own expanding ring. These rings sit one inside the other, like the layers of an onion lit from within. The Cat's Eye Nebula is one of the most complex examples known. Its intricate rings and jets and knots suggest the star that made it went through many separate eruptions, each one adding another layer to the structure. Scientists are still working to understand exactly how it formed. There are also nebulae with jets. Vast streams of gas shoot outward from the poles of the central star, sometimes at speeds of hundreds of kilometers per second. These jets can punch through the surrounding gas cloud and create long, narrow extensions that stretch far beyond the main body of the nebula. The result looks almost like a star with rays, or a glowing spindle floating in the dark. What is remarkable is that all of these shapes, the spheres, the hourglasses, the rings, the multi-shelled structures, the jet-driven forms, all of them come from the same basic process. A star runs out of fuel. It swells. It sheds its outer layers. A white dwarf ignites the gas, and yet the outcome is never quite the same twice. The spin of the star, the speed of the stellar wind, the presence of a companion star nearby, the density of the surrounding space. All of these factors combine to produce something unique. The same process, repeated across billions of stars over billions of years, never repeats itself exactly. This is one of the quiet rhythms of the universe. Stars are born, they burn, they swell and shed and collapse. The cycle runs again and again across every galaxy. But within that cycle, within that repeating pattern, there is endless variation. Every planetary nebula is a single moment in that cycle, caught in a shape that no other star has made before, and no other star will make again. And so we find ourselves asking a natural question. If the same basic process creates every planetary nebula, what makes each one so different from its neighbors? The answer begins not with the dying star itself, but with everything around it. Space is not empty. Even the vast stretches between stars hold thin clouds of gas and dust, left over from ancient explosions and slow stellar winds that drifted outward long ago. When a star begins to shed its outer layers, those layers do not expand into a perfect vacuum. They push into whatever is already there. If the surrounding gas is dense in one direction and thin in another, the expanding shell will slow down on one side and race ahead on the other. The result is a shape that bends and stretches, pulled by the uneven resistance of its own neighborhood. Think of it like blowing a soap bubble inside a room where the air pressure is different in every corner. The bubble would not come out round. It would bulge where the pressure is low and flatten where the pressure is high. Planetary nebulae do something very similar on a scale of trillions of miles. The density of the space surrounding a dying star is shaped by the star's own history. During its long life on the main sequence, a star pushes a slow, steady wind of particles outward into space. This wind carves out a wide, thin bubble around the star called the circumstellar envelope. When the star later swells into a red giant and begins shedding mass more rapidly, that new, faster wind slams into the older, slower material already sitting nearby. The collision creates a compressed shell, like a wave building up against a sandbar. The shape of that shell depends entirely on how the earlier wind was was distributed. If the slow wind was thicker around the star's equator, the compressed shell will be thicker there too, and the nebula will take on a flattened, disc-like form. Magnetic fields also play a quiet but powerful role. Stars generate magnetic fields, and those fields can direct where gas flows as it leaves the stellar surface. A strong magnetic field near the poles of a dying star can funnel gas into narrow jets, while gas near the equator spreads outward more freely. Scientists believe this is one reason so many planetary nebulae show elongated or bipolar shapes, stretched along one axis like a glowing peanut, or a pair of bright lobes facing each other across the dark. The rotation of the star adds another layer of variation. A star that spins quickly will fling more material outward from its equator due to centrifugal force. The same tendency that makes a spinning ball of wet clay flatten at the top and bulge at the middle. A slowly rotating star sheds its layers more evenly in all directions. The spin rate of a star is set early in its life and changes over billions of years. So by the time a star reaches the end of its life, its rotation carries the full memory of everything that shaped it along the way. Even the chemical makeup of the surrounding space leaves its mark. Some stars spend their lives near regions where previous generations of stars have already scattered heavy elements like carbon, oxygen, and nitrogen into the gas clouds nearby. When a new dying star expands into that enriched neighborhood, its nebula will contain a different mix of materials than a nebula expanding into a cleaner, older region of the galaxy. Those differences show up in the colors the nebula glows, in the way its gas responds to ultraviolet light, and in the fine structure of its edges. All of these influences, the surrounding gas, the old slow wind, the magnetic field, the spin, the chemical neighborhood, act on the nebula at the same time. They do not take turns. They push and pull together, each one shaping the outcome in ways that interact with all the others. A small change in any one of them shifts the final form in ways that ripple through the whole structure. This is why astronomers who study planetary nebulae sometimes describe their field as looking at a gallery where every painting was made with the same brushes tools are the same. The process is the same. And yet the results are endlessly different. The universe does not repeat itself, even when it follows its own rules. It takes the same ingredients, the same forces, the same ancient cycle of birth and death, and finds a new arrangement every single time. Each nebula floating in the dark is a shape that exists only once, in one place, at one moment in the long life of the cosmos. And yet, for all that variety, there is one force that can push a planetary nebula far beyond anything a single star could make on its own. That force is a companion, a second star orbiting close, changes everything. Most stars in the universe do not live alone. More than half of all stars are part of pairs or small groups, bound together by gravity, circling each other across vast stretches of time. When one of those paired stars begins to age and swell into a red giant, the presence of its companion does not simply add a small detail to the story. It rewrites the story entirely. A single aging star tends to shed its outer layers in a slow, mostly even way. The result is often a round or gently oval nebula, glowing softly in the dark. But when a companion star is nearby, it pulls on those outer layers as they drift away. It tugs at the gas, bends the flow, and sometimes strips material away in great rushing streams. The nebula that forms from this process can be wildly different from anything a lone star produces. It can be stretched into long lobes, twisted into spirals, or shaped into hourglass forms that look almost too precise to be natural. Some companion stars orbit so close to the aging giant that something even more dramatic happens. The giant swells so large that its outer atmosphere actually surrounds both stars. The two stars are then inside a shared envelope of gas, orbiting each other within it. This is called a common envelope phase, and it is one of the most violent and short-lived events in stellar life. The two stars spiral inward toward each other. The shared gas is flung outward at tremendous speed. What remains after this brief, fierce event is a tight pair of stars wrapped in an expanding shell of gas that glows with extraordinary brightness and symmetry. hourglass shape seen in some of the most striking nebulae in the sky is thought to come from exactly this kind of event. The speed at which gas moves in these companion-driven nebulae can be staggering. In a typical planetary nebula, the outer shell of gas expands at roughly 10 to 20 kilometers per second. That is already fast enough to cross the entire distance from Earth to the Moon in about 20 seconds. But in nebulae shaped by close companion stars, jets of gas can shoot outward at hundreds of kilometers per second. These jets are narrow, focused, and extraordinarily powerful. They carve long, bright channels through the surrounding gas, leaving structures that look like the beams of a lighthouse, frozen in time. There is a nebula called the Butterfly Nebula, known to astronomers as NGC 6302. That shows what a companion's influence can produce at its most extreme. The gas in its wings is moving at more than 600 kilometers per second. That makes it one of the fastest expanding planetary nebulae ever measured. The star at its center is also one of the hottest known white dwarfs, with a surface temperature estimated at around 200,000 degrees Celsius. That is nearly 40 times hotter than the surface of our own sun. The combination of extreme heat and extreme speed fills the butterfly's wings with a fierce, brilliant glow. Companion stars can also affect the timing of a nebula's formation. In some cases, a companion pulls mass away from the aging star before it is ready to shed its layers naturally. This can trigger the formation of a nebula earlier than it would otherwise occur, or cause the dying star to release its gas in repeated pulses rather than one long, slow breath. Some nebulae show multiple shells, one inside another, like rings on the surface of a pond, after several stones have been dropped in sequence. Each ring marks a separate episode of mass loss, each one triggered or shaped by the companion's gravitational pull. Even after the nebula has formed and begun to fade, a companion star can keep the central white dwarf active. Material from the companion can fall onto the white dwarf surface, heating it and causing it to shine more brightly than it would on its own. This keeps the surrounding gas lit longer than usual, extending the visible life of the nebula by thousands of years, the presence of a second star does not complicate the story of a planetary nebula. It deepens it. It adds another voice to what was already a rich and layered process. Two stars, bound together across billions of years, reach the end of one life and leave behind something more intricate, more vivid, and more strange than either could have made alone. The universe, it seems, saves some of its most remarkable work for those who do not travel through it by themselves. Some of the most remarkable things in the universe are also the closest. You do not always have to look far to find something worth pausing over. A few planetary nebulae sit relatively near to our own solar system, and because of that closeness, scientists have been able to study them in extraordinary detail. The small things become visible. The fine textures, the faint outer halos, the subtle shifts in color from one edge to the next. Closeness is a gift in astronomy, and these nearby nebulae have given us more than most. The Helix Nebula is the closest planetary nebula to Earth that is easily visible to telescopes. It sits roughly 650 light years away in the constellation Aquarius. That sounds impossibly far, and in everyday terms it is. But in the scale of the galaxy, it is practically next door. Because of that closeness, the helix appears larger in the sky than almost any other planetary nebula we know. If you could see it with your naked eye, it would cover an area nearly as wide as the full moon. It is an enormous structure, stretching across roughly 3 light years from one edge to the other. What makes the helix especially striking is what lives inside it. Astronomers, using the Hubble Space Telescope, found thousands of small, dense knots of gas scattered throughout the nebula's inner ring. Each knot has a bright head and a long, faint tail pointing away from the central white dwarf, like a comet frozen in place. Scientists call these structures cometary knots, though they have nothing to do with actual comets. Each one is roughly the size of our entire solar system. There are an estimated 40,000 of them in the helix alone. They are thought to form where fast-moving gas from the dying star crashes into slower, older gas that was shed earlier in the star's life. The collision creates ripples, and the ripples form knots. The helix is not a simple ring either. Early observations made it look like a single loop of glowing gas, but deeper study revealed it has at least two overlapping disks of material, tilted at different angles to each other. Seen from the side, they would look like two rings crossing. Seen from above, as we see them, they overlap and create the illusion of one smooth structure. The helix is quietly more complex than it first appears. Not far behind the helix, in terms of closeness, is the Cat's Eye Nebula. Located about 3,300 light-years away in the constellation Draco, it is one of the most studied planetary nebulae in the sky, partly because of its position and partly because of what Hubble revealed when it looked closely. The Cat's Eye has at least 11 concentric shells of gas surrounding its bright inner core. Those shells are nearly evenly spaced, like growth rings inside an ancient tree. Scientists believe they were produced by pulses of material released from the central star roughly every 1,500 years. Each shell is a record of a moment in that star's long, slow unraveling. The central white dwarf of the Cat's Eye is one of the hottest known, with a surface temperature estimated at around 80,000 degrees Celsius. That intense heat floods the surrounding gas with ultraviolet light, causing it to glow in vivid shades of blue and green. The inner region burns with a bright, almost electric teal. The outer shells are softer, more diffuse, fading gradually into the dark. Up close, through a powerful telescope, the Cat's Eye looks like something carved with great care, layer by layer, over thousands of years. Closer still in some measurements is the Dumbbell Nebula, sitting about 1,360 light-years away in the constellation Vulpecula. It was the first planetary nebula ever discovered, though that story belongs to a later section. What matters here is its shape. The dumbbell looks, as its name suggests, like two lobes of gas pushing outward from a central point, like a figure 8 or an apple core seen from the side. The lobes glow in warm shades of green and pink, with faint outer wings of gas extending beyond the main structure. It is one of the brightest planetary nebulae in the sky, and one of the easiest to observe with even a modest telescope. They are close enough that we can read their details the way you might read the grain of wood in a table you are resting your hands on. Each one holds a slightly different story. Each one shows a different way a star can end. And all three are out there tonight, glowing quietly in the dark, waiting to be noticed. The Dumbbell Nebula holds a special place in the history of astronomy. It was the first planetary nebula a human being ever recorded seeing through a telescope. That moment happened in the summer of 1764 in France, when a man named Charles Messier turned his telescope toward the constellation Vulpecula and saw something he could not quite explain. Messier was not looking for nebulae. He was hunting comets. Comets were the great prize of 18th century astronomy, and Messier was one of the best comet hunters of his age. But fuzzy, glowing patches of light kept fooling him. They looked like comets at first glance, soft and diffuse against the sharp points of stars. So Messier did something practical and generous. He began making a list of all the things that were not comets, so that other astronomers would not be confused by them. The Dumbbell Nebula became the very first entry on that list. It is known today as Messier 27, or simply M27. Messier had no idea what it was. He described it as an oval nebula without stars. He moved on, looking for comets, but the object he catalogued that night would turn out to be one of the most important things in the sky. The catalog Messier built eventually grew to over 100 objects. Many of them are now among the most studied and most photographed things in the universe. The Ring Nebula in the constellation Lyra became Messier 57. The Owl Nebula in Ursa Major became Messier 97. Neither Messier nor his colleagues understood what these glowing ovals truly were. They simply noted them, named them by number, and kept searching for comets. The real nature of these objects would remain a mystery for decades. The man who gave Planetary Nebulae their name was William Herschel, the German-born British astronomer who also discovered the planet Uranus. Herschel was a tireless observer. He spent long nights sweeping the sky with telescopes he built himself, cataloging everything he found. When he looked at objects like the one Messier had recorded, he noticed that some of them in 1785, not because he thought they had anything to do with planets, but because of how they looked through his telescope. The name stuck, even after scientists understood that planets had nothing to do with them at all. Herschel himself was not certain what he was seeing. He wondered if some planetary nebulae might be very distant star clusters, too far away to resolve into individual points of light. Others, he thought, might be some kind of luminous fluid filling space. He was wrong about the details, but he was asking exactly the right questions. His careful records and his willingness to say, "I do not know," helped later astronomers build on his work. The Ring Nebula became one of the most studied of all. It sits in the small constellation Lyra, not far from Vega, one of the brightest stars in the northern sky. Through a small telescope, it looks like a tiny smoke ring, a pale circle of light with a darker center. Through larger instruments and modern cameras, it reveals itself as a glowing shell of gas in shades of blue, green, and red, with a faint white dwarf star visible at its heart. For a long time, astronomers debated whether the ring was truly a shell seen from outside, or a tube of gas seen end on, like looking down the barrel of a glowing cylinder. Recent observations suggest the true shape is more complex than either idea. Something like a distorted torus, which is the shape of a donut, with additional layers of gas extending outward in ways that are still being studied. The Owl Nebula earned its name much later, in the 19th century, when the Irish astronomer Lord Rosse observed it through his enormous telescope at Birr Castle and saw what looked like two dark eyes staring back at him. The telescope Lord Rosse built, called the Leviathan of Parsonstown, was the largest in the world for several decades. It had a mirror 6 feet across, made of a metal alloy, and it took dozens of workers to move and aim. With it, Lord Rosse could see details in nebulae that no one had ever seen before. He was the first to notice the spiral structure in certain distant galaxies, and when he turned it toward the Owl Nebula, he sketched what he saw with careful, patient lines, the way a naturalist might draw a bird or a flower, trying to capture something true about the world. These early astronomers worked without cameras, without computers, without any of of the tools we take for granted today. They worked by eye, by hand, and by the slow accumulation of careful observation over lifetimes of work. Those early astronomers had no word for what they were looking at. When William Herschel first turned his telescope toward certain glowing patches in the night sky, he had to reach for the closest description he could find. They looked round. They looked soft at the edges. They looked, in some ways, like the pale disk of a distant planet seen through a modest telescope. So in 1785, Herschel gave them a name, Planetary Nebulae. He knew they were not planets. He said so himself. But the name stuck, and we still use it today, even though it tells us almost nothing true about what these objects actually are. This is one of the great quiet surprises in the history of astronomy. A name chosen for pure convenience, based on a visual resemblance that has nothing to do with the underlying reality, has outlasted centuries of discovery. Planetary nebulae have no connection to planets whatsoever. They are the shed outer layers of dying stars. But Herschel's label was simple and easy to remember. And science, like everything else, carries its history forward. Herschel himself was a remarkable figure. He was born in Germany and trained as a musician before he became one of the greatest observers in the history of astronomy. He ground his own telescope mirrors by hand, sometimes working for hours without stopping. His sister Caroline holding food to his mouth so he would not have to pause. With those handmade instruments, he discovered Uranus, catalogued thousands of stars, and began to map the shape of the Milky Way. He was the first person to understand that the sun itself moves through space, carried along with all its neighboring stars in a slow drift across the galaxy. When Herschel catalogued his planetary nebulae, he listed dozens of them. He was not certain what they were made of. He considered the possibility that they might be vast clouds of a glowing fluid, something like a luminous gas, spread across enormous distances. This was a genuinely bold idea for his time. Most astronomers assumed that anything glowing in the sky must be made of stars too faint and too distant to resolve individually. The idea that a cloud of gas could shine on its own was strange and new. The confirmation came decades later, in 1864, when the English astronomer William Huggins pointed a new kind of instrument at a planetary nebula. That instrument was a spectroscope, a device that spreads light apart into its component colors the way a prism does, revealing a kind of fingerprint that identifies what the light is made of. When Huggins examined the Cat's Eye Nebula, he expected to see the blended rainbow of countless distant stars. Instead, he saw something completely different. He saw a few bright, sharp lines of color against a dark background. That pattern was the unmistakable signature of glowing gas. In a single observation, Huggins confirmed that planetary nebulae were not unresolved clusters of stars. They were clouds of actual gas, shining in the dark. Huggins described the moment with quiet astonishment. He wrote that he felt he had passed into a region that was different in kind from anything previously known. That is a careful, measured way of saying that the universe had just revealed something unexpected. The spectroscope would go on to transform astronomy entirely, giving scientists a way to measure not just what distant objects are made of, but how fast they are moving and how hot they are. Huggins had opened a door that would never close again. What makes this history feel so alive is how recent it all is. The correct understanding of what planetary nebulae actually are. Dying stars releasing their outer layers, while a white dwarf forms at the center, did not fully come together until the 20th century. For most of human history, these glowing rings and shells were simply beautiful mysteries. People looked at them and named them after owls and cats and dumbbells and rings, reaching for familiar shapes to hold onto something they could not yet explain. And even now, with space telescopes and spectrographs and computers that can model the physics of stellar winds, planetary nebulae still surprise the scientists who study them. Their shapes are stranger than expected. Their chemistry is richer than models predict. The more closely we look, the more complexity we find hiding inside what first appeared to be simple glowing rings. Herschel saw a round, soft glow and called it planetary. Huggins saw bright lines in a spectroscope and understood it was gas. Each generation looks a little deeper each time, the universe offers something new to wonder at. Each generation of scientists has looked at planetary nebulae with better eyes than the last. And the tools they have built to do that looking are themselves a kind of wonder. For most of history, the only instrument available was the human eye pressed against the end of a telescope. That was enough to see that something glowing and round was out there. But it was not enough to understand what it was. The eye alone cannot tell you what something is made of. It cannot measure temperature or distance or motion. It can only say, something is there and it is beautiful. The spectrograph changed everything. A spectrograph is a device that splits light into its separate colors. The way a prism spreads sunlight into a rainbow. Every element in the universe, when heated to a gas, releases light at its own specific set of colors. Hydrogen glows at one set of wavelengths. Oxygen glows at another. Nitrogen at another still. When you pass the light from a planetary nebula through a spectrograph, you get a kind of fingerprint. You can read exactly what the nebula is made of, just from the colors of its glow. This is the same technique William Huggins used in 1864, and scientists still use it today, though the instruments are now far more precise. Modern spectrographs can be attached to telescopes the size of buildings. The Very Large Telescope in Chile, sitting high on a dry desert mountain called Cerro Paranal, uses mirrors more than 8 meters across to gather light from objects billions of light years away. When that telescope turns toward a planetary nebula, it can detect chemical signatures so faint they would have been completely invisible to any instrument built before the 20th century. It can measure how fast the gas is moving, which direction it flows, and how the density of the shell changes from the inner edge to the outer rim. Radio telescopes add another layer. Planetary nebulae do not only glow invisible light, they also emit radio waves, a form of light the human eye cannot see at all. Radio telescopes, which look like enormous satellite dishes pointed at the sky, can detect these invisible signals. They reveal structures inside nebulae that optical telescopes miss entirely. Some nebulae have faint outer halos of gas that extend far beyond what we can see with visible light. Radio observations have found these halos drifting quietly in space, remnants of stellar winds that blew outward thousands of years before the nebula itself formed. Then there is infrared light, which sits just beyond the red end of the visible spectrum. Dust inside a planetary nebula absorbs visible light and re-emits it as infrared radiation. Infrared telescopes can see through that dust and reveal the hidden structure beneath. The Spitzer Space Telescope, which operated from 2003 to 2020, captured infrared images of planetary nebulae that showed warm dust rings and shells invisible to any other instrument. Some of those images revealed that nebulae thought to be simple and round were actually far more complex, with layered shells nested inside one another like the rings of a cut onion. The Hubble Space Telescope sits above Earth's atmosphere, which blurs and distorts light before it reaches the ground. From its position in orbit, Hubble can capture images of extraordinary sharpness. Its photographs of planetary nebulae are among the most detailed images of any object in the sky. The Cat's Eye Nebula, the Butterfly Nebula, the Helix Nebula. These became iconic partly because Hubble showed them in a clarity no ground-based telescope could match. Hubble revealed jets of gas shooting outward from central stars, rings within rings, and knots of dense gas scattered through the glowing shells like seeds. The James Webb Space Telescope, launched in December 2021, has pushed even further. Webb observes primarily in infrared light, and its mirror is more than 6 meters across. In 2023, Webb captured a new image of the Ring Nebula, one of the most studied objects in the sky, and revealed details no one had seen before. Faint arcs of gas in the outer halo, tiny dense knots at the inner edge of the ring, structures so fine they had been invisible even to Hubble. A nebula studied for more than 2 centuries still had things left to show. Each new instrument is a new kind of eye. Each wavelength of light tells a different part of the same story. Visible light shows the glow. Infrared shows the dust. Radio waves show the faint outer edges. Spectrographs show the chemistry. single tool could create alone. The nebula has always been there, patient and glowing. We are simply learning slowly how to look. Inside the glowing shells of a planetary nebula, things are not still. They only look that way from here. The gas that a dying star throws outward does not simply drift and fade. It moves. It changes shape. It collides with itself. The inner shells, pushed by faster winds from the hot white dwarf at the center, travel outward more quickly than the outer shells. When faster gas catches up to slower gas, it piles up. It forms dense ridges and bright rims, like the bow wave in front of a slow-moving boat. Astronomers call this process the interacting stellar winds model. It explains why so many planetary nebulae have that sharp, clean inner edge, bright and well-defined, glowing against the darker gas beyond. Those bright inner rims are not fixed. They are expanding right now, pushing outward at speeds that can reach tens of kilometers per second. That sounds fast, but a planetary nebula is enormous. Even at that speed, the visible change across a human lifetime is tiny. Astronomers measure the expansion not by watching it happen in real time, but by comparing photographs taken decades apart. When they line up an image from the 1990s beside one taken today, they can see the shell has grown. Just slightly, just enough to measure. The nebula is breathing outward, one slow breath across 1,000 years. Some of the most striking features inside a nebula are the knots. These are small, dense clumps of gas that form when the fast inner wind slams into the slower outer material. The collision is not smooth. It breaks up into hundreds or thousands of individual blobs, each one dense enough to resist being blown apart. The Helix Nebula, one of the closest planetary nebulae to Earth, contains more than 20,000 of these knots. Each one is roughly the size of our entire solar system. They trail faint tails of gas behind them, pointing away from the central star like the tails of comets. Scientists sometimes call them cometary knots for exactly that reason. These knots are not just beautiful. They are places where chemistry happens. Inside the dense gas of a knot, molecules can form. Simple ones at first, like hydrogen molecules, where two hydrogen atoms bond together. Then more complex ones: carbon monoxide, water, even organic molecules, the carbon-based building blocks that life on Earth depends on. A planetary nebula is not just a cloud of loose atoms. In its densest regions, it is a slow chemistry lab, building molecules in the dark between the glowing shells. Dust forms there too, not the dust on a windowsill, but tiny solid grains, smaller than a grain of sand, made of carbon or silicates, the same minerals found in rocks. These grains condense out of the cooling gas as it moves away from the hot central star. They are dark and solid, and they absorb light rather than emit it. That is why infrared telescopes, like the James Webb Space Telescope, see so much more than optical ones. Dust that blocks visible light glows in infrared. Webb can trace the dust lanes and shells that are completely invisible to the human eye, revealing structure hidden inside structure, layer after layer. The white dwarf at the center is changing too. It is cooling, slowly, patiently, over billions of years. It radiates its stored heat into space. As it cools, the ultraviolet light it sends into the nebula weakens. That light is what powers the glow. It strips electrons from atoms in the gas, and when those electrons fall back into place, they release light. As the white dwarf fades, it loses the power to keep the gas lit. The nebula begins to dim. The colors soften. The sharp edges blur. The gas spreads thin. This is the long, quiet ending. Not a sudden darkness, but a slow dissolving. The gas drifts outward until it is too spread out to glow. It blends into the surrounding space between the stars, that vast, cold, nearly empty region called the interstellar medium. What was once a brilliant ring of color becomes invisible. The atoms are still there. The carbon, the oxygen, the nitrogen, they have not gone anywhere. They are simply waiting, mixed into the great slow cloud of material that fills the space between stars. Everything the nebula was, it gives away. Every molecule it built, every grain of dust it formed, every atom it scattered, all of it becomes part of the raw material of the galaxy. The change is total. The change is patient. And the change, in the end, is generous beyond A planetary nebula does not last forever. Nothing in the universe does. But the question of how long one lasts is one of the most beautiful and precise things astronomers have measured. These glowing clouds of gas are not permanent fixtures in the sky. They are moments, long moments by human standards, but brief ones by the standards of the cosmos. Most planetary nebulae last somewhere between 10,000 and 30,000 years. That sounds like a long time. But our sun is nearly 5 billion years old. Compared to that, a planetary nebula is like a single breath. A soft, luminous exhale that fades before the universe has barely noticed it began. The light is what drives everything, and the light is always running out. When a white dwarf first forms at the center of a nebula, it burns at extraordinary temperatures. Some white dwarfs reach surface temperatures of over 100,000 degrees Celsius in their earliest stages. That is nearly 20 times hotter than the surface of our own sun. At those temperatures, the white dwarf pours out enormous amounts of ultraviolet light, the high-energy kind that strips electrons from atoms in the surrounding gas. This process is called ionization. It is what makes the nebula glow. The colors that pour out of a planetary nebula are not random. They are a direct record of what the light is doing at each moment. Hydrogen gas, when ionized and then recombining, releases a deep red glow. Oxygen, when it absorbs and re-emits energy, produces a blue-green color that astronomers call aqua, or sometimes teal. Nitrogen adds its own warm red tones. The result is a layered painting made of physics, where each color marks a different gas at a different distance from the central star. The blue and green regions tend to sit closer to the white dwarf, where the ultraviolet light is strongest. The red regions drift further out, where the energy has weakened just enough to produce a different kind of glow. So as you look at a planetary nebula from the outside in, you are reading a map of the light's reach. You are watching energy travel and fade in real time, frozen into color. But the white dwarf is cooling. It cannot help it. There is no fuel left to burn. A white dwarf generates no new energy through nuclear fusion. It simply radiates the heat it already holds, like an ember pulled from a fire. Slowly, steadily, it loses that heat to the surrounding darkness. As the white dwarf cools, its ultraviolet output drops. The ionizing light grows weaker. The gas in the nebula begins to recombine without being stripped apart again. The glow softens. The vivid blues and greens fade first, because those colors need the most energetic light to form. The reds linger a little longer. Then they too begin to dim. At the same time, the gas itself is moving. It has been expanding outward since the moment the nebula formed, pushed by the pressure of the stellar wind from the dying star. A typical nebula expands at speeds of around 10 to 30 kilometers per second. That is fast enough to cross the distance between Earth and the Moon in about 15 seconds. Over thousands of years, this steady outward drift carries the gas further and further from the white dwarf. The density drops. The gas thins, and thin gas glows less brightly, even when light still reaches it. These two forces work together. The cooling white dwarf sends less light. The expanding gas grows less dense. The nebula dims from both ends at once, the source weakening and the material spreading until the glow simply cannot sustain itself. What remains visible to our telescopes is only the brightest phase of a much longer story. We see planetary nebulae at their peak, when the colors are sharpest and the light is strongest. But astronomers know that for every nebula we can see, there are many more that have already faded past the point of detection. They are still out there, their atoms drifting through the space between stars, invisible and patient. The light tells us everything. It tells us how hot the central star is, how far the gas has spread, which elements are present, and how much time has passed since the star first let go. Every color is a clue. Every shift in brightness is a measurement. The nebula writes its own history in light, and we read it with our telescopes from billions of kilometers away. It is a remarkable thing to read the age of a dying star by the color of its glow. The universe leaves its records in light, and we have learned slowly and carefully how to read them. Light is not the only record the universe keeps. Even in the deep silence of space, where no air carries sound, there are vibrations, there are waves, There are pulses that instruments can detect and translate into something our ears can understand. And when scientists do this with planetary nebulae, what they find is extraordinary. The white dwarf sitting at the center of a planetary nebula is not always still. Some white dwarfs pulse. They expand and contract in tiny, rapid cycles, like a heart beating in slow motion. These pulses change the brightness of the star in a regular rhythm. Astronomers call these stars pulsating white dwarfs, and they have been studied carefully for decades. The rhythm of the pulse tells scientists what the star is made of, how thick its outer layers are, and how it is cooling over time. When scientists convert those brightness changes into sound, the result is a low, steady tone. It rises and falls. It shifts. It is not random noise. It has structure. It has pattern. The white dwarf is, in a very real sense, ringing like a bell that was struck millions of years ago and has not yet gone quiet. This technique has a name. It is called astrocosmology, which means the study of vibrations inside stars. The same way geologists use earthquake waves to learn what is deep inside the earth. Astronomers use stellar vibrations to learn what is deep inside a star. The waves travel through the interior of the white dwarf and carry information about its layers, its density, and its temperature. Each vibration is a message written in motion. The Kepler Space Telescope, which was designed to find planets by watching for tiny dips in starlight, also captured the pulses of white dwarfs in extraordinary detail. Kepler watched some of these stars for months without blinking, recording every tiny flicker. Scientists then took those brightness records and turned them into audio files. The sounds are eerie and soft. Some white dwarfs produce a single clear tone. Others produce a chord, several frequencies layered on top of each other, because different parts of the star vibrate at different rates. The gas shell surrounding the white dwarf also carries motion. The nebula itself is not still. The gas is moving outward, always expanding, pushed by the pressure of the stellar wind and the radiation pouring from the hot star at the center. That outward motion creates its own kind of wave. When the fast inner wind catches up to the slower outer gas, it creates a shock. a sudden compression where the two meet. Shock waves in gas produce pressure changes. Pressure changes, translated into sound, produce a low rumble. If you could somehow stand near the edge of a planetary nebula and feel the vibrations rather than hear them, it would feel like the deep, slow trembling of something enormous slowly passing by. Scientists have also detected something called infrared echoes inside some nebulae. As the radiation from the central star moves outward through the gas, it heats dust grains along the way. That heating happens at slightly different times depending on how far the dust is from the star. The result is a ripple of warmth that moves through the nebula like a slow wave. When mapped over time, these infrared echoes look like rings spreading outward from a stone dropped into still water. They carry information about how the star shed its layers, how fast the wind moved, and how the gas was distributed. There is something deeply moving about this. A star that has been silent for tens of thousands of years is still sending out signals. Its light has faded. Its gas has spread thin, but the vibrations it set in motion are still traveling. The ripples are still moving. The bell is still ringing quietly at a frequency too low for any human ear, but perfectly readable by the instruments we have built and placed in orbit above our atmosphere. The universe does not simply end things, it transforms them. A star burns for billions of years, then swells, then releases its outer layers in a slow, glowing cloud. The white dwarf at the center cools and pulses. The gas expands and shocks and ripples, and all of it, every stage, leaves a record. In light, in heat, in vibration, in the slow drift of atoms through the dark. We have built the tools to read those records, and what we find every time is that nothing in the universe goes quietly. Even the fading of a star is full of information. Even the silence has a sound. The universe is always speaking. We are only just learning how to listen. And woven into every signal, every ripple, every fading pulse of light, there is something else. Something you can measure, something you can count. The dying star has not only sent out waves of energy, it has sent out the actual building blocks of matter itself, the elements that scientists can calculate and predict with quiet confidence. When a star sheds its outer layers, it releases a mixture of elements in specific ratios. Hydrogen is always the most abundant. It makes up roughly the same large fraction of the cloud, no matter which star created it. Helium comes next. Then, in smaller but deeply important amounts, come the heavier elements: carbon, nitrogen, oxygen. These three are the ones that matter most for life as we know it. A single planetary nebula can release more oxygen into space than our entire sun contains right now. That number is worth sitting with for a moment. The oxygen you breathe tonight, the oxygen dissolved in every ocean on Earth, traces a line back to events like this one. Stars that lived and swelled and let go long before our sun was born. The math tells us that roughly half of all the carbon now drifting through the Milky Way was made inside stars like these, in the slow nuclear burning that happens deep in a red giant's core. Half of all the carbon in the galaxy, released grain by grain into the dark. The process that makes these elements is called nucleosynthesis, which simply means the building of new atomic nuclei inside a star. In the final stages of a star's life, temperatures in the core can reach 100 million degrees or more. At those temperatures, helium atoms fuse together in a precise sequence. 3 helium nuclei combine to form 1 carbon nucleus. This is called the triple alpha process because helium nuclei are also known as alpha particles. The numbers here are extraordinary. The energy levels of carbon just happen to align in a way that makes this reaction possible. If they were even slightly different, carbon would almost never form. The universe would be a very different and far emptier place. From carbon, the star can build oxygen. From oxygen, it can build nitrogen. Each step follows a chain of reactions, each one governed by the same physical constants that have held steady since the first moments after the universe began. The ratios of these elements in a planetary nebula's cloud are not accidental. They are the direct output of billions of years of nuclear math carried out in the heart of a star and then released all at once in a slow, glowing spectroscopy, which means reading the unique pattern of light that each element produces. Every element absorbs and emits light at specific wavelengths, specific colors, like a fingerprint. When astronomers point a spectrograph at a planetary nebula, they can read the chemical recipe of that cloud with remarkable precision. They can tell you not just what elements are present, but in what proportions, and even at what temperatures those elements are glowing. The Helix Nebula, that vast glowing ring about 650 light years away, has been studied this way in great detail. Its cloud contains oxygen, hydrogen, nitrogen, and carbon in ratios that match the predictions of stellar models almost exactly. The math written in the light matches the math worked out on paper. That agreement between theory and observation is one of the quiet triumphs of modern astronomy. There is something almost musical about it. The universe runs on a small set of rules. Those rules produce the same outcomes again and again across billions of stars and billions of years. A star of a certain mass, burning for a certain length of time, will produce a certain mix of elements. You can predict it. You can calculate it. And when you look, you find exactly what the equations said you would find, glowing softly in the dark, hundreds of light years away. The elements drift outward from the nebula at speeds of 10 to 30 kilometers per second. Slowly, by cosmic standards, but over tens of thousands of years, they spread across enormous distances. They mix with the existing gas between the stars. They cool. They condense. They become part of the raw material from which new stars and new planets will one day form. The math that governed their creation inside a dying star now governs their journey through the dark. Numbers do not stop when the star does. They just move on, carrying their precise and patient instructions into the next chapter of the universe's long, unfolding story. And so those drifting elements do not simply wander forever. They are heading somewhere. They have a purpose, though the universe does not plan it. It simply works out that way every time, with quiet and patient precision. The gas and dust released by a dying star eventually reaches the cold, thin clouds that float between the stars. These clouds are called the interstellar stellar medium. They are not empty. They are full of hydrogen, helium, and trace amounts of heavier elements, some of which arrived from older planetary nebulae that dissolved long before our sun was born. When fresh material from a new nebula drifts into one of these clouds, the cloud grows a little richer, a little more complex, a little more ready. What happens next depends on a very fragile balance. The cloud must be cold enough to collapse under its own gravity. It must be dense enough that gravity wins over the pressure pushing outward. It must contain just the right amount of mass. Too little, and the cloud simply drifts apart. Too much, and it collapses too fast, producing a massive star that burns hot and dies young before planets have time to form and cool. The window for a star like our sun, a calm and steady star that burns for billions of years, is surprisingly narrow. Carbon, nitrogen, and oxygen from planetary nebulae play a direct role in helping clouds cool down. When a cloud cools, it can collapse more easily. These elements radiate heat away from the cloud, letting gravity slowly take hold. Without them, many clouds would stay too warm and too diffuse to ever form a star at all. The elements scattered by a dying star are not just passengers in the next generation. They are part of the engine that starts it. Once a new star ignites, the leftover material around it begins to flatten into a spinning disk. Dust grains in that disk stick together. They grow from tiny specks into pebbles, from pebbles into rocks, from rocks into the early building blocks of planets. The carbon and silicate dust that came from planetary nebulae is part of this process. It is the raw material of worlds, the same atoms that once glowed in a ring of colored light around a white dwarf are now pressing together in the dark, slowly becoming something solid. The distance at which a planet forms matters enormously. Too close to the new star, and it is too hot for water to stay liquid on the surface. Too far, and it is too cold. There is a narrow band around every star where liquid water can exist. Scientists call this the habitable zone. Earth sits inside that band with almost no room to spare. A small shift in our orbit in either direction would change everything. The atmosphere matters just as much. Earth's thin dozen miles thick compared to a planet nearly 8,000 miles wide, traps enough heat to keep the surface warm. It blocks enough radiation to keep life safe. The nitrogen in that atmosphere was forged in stars. The oxygen was released by early life, but the nitrogen was there first, drifting down through billions of years of stellar recycling, arriving here long before the first living thing drew a breath. Even the carbon in every living cell on Earth passed through this same long chain. It was made in a star. It was released in a nebula. It drifted through cold space. It fell into a young solar system. It became rock, then ocean, then life. Every step of that chain had to work. Every condition had to be met. The temperature, the chemistry, the timing, the distance from the sun. All of it had to land within a narrow range. The fact that it did is not magic. It is probability stretched across billions of stars and billions of years. Most of those stars produce conditions that never lead to life, but some do. And the planetary nebulae that came before our sun helped tip the odds. They seeded the cloud that became our solar system with exactly the elements that complex chemistry requires. There is something quietly astonishing about that. The death of a star you will never see, in a place you will never visit, that ended billions of years before you were born, made you possible. It sent its atoms out into the dark. Those atoms cooled and gathered and collapsed and burned and eventually became the ground beneath your feet, the air in your lungs, the carbon in your bones. The universe did not plan any of this. It simply followed its rules, one careful step at a time, and arrived here anyway. And yet, for all we understand about that chain of events, there is still so much we do not know. The story of planetary nebulae and our own solar system is not finished. Scientists are still filling in the gaps, still asking questions that have no clean answers yet. That is not a failure of science. It is science working exactly as it should. One of the biggest open questions is this: which specific stars, in which specific nebulae, contributed material to our solar system? We know the sun formed inside a giant cloud of gas and dust. We know that cloud contained elements forged in dying stars, but we cannot point to a single nebula, and say with certainty, that one, that star, that is the one whose death helped make us. The trail is too old, the evidence too scattered. Scientists are still working to understand which types of stars were most likely nearby when our sun was born. There is a clue, though. Deep inside certain meteorites, the oldest rocks in our solar system, scientists have found tiny grains of material that formed inside ancient stars before our sun existed. These grains are called presolar grains. They survived the formation of the solar system without being melted or mixed away. They are, in a sense, fossils of the stars that came before us. When scientists study these grains, they can read the chemical fingerprints of those long-dead stars. It is one of the most remarkable things in all of science. A rock that fell from the sky carries the remains of a star that died before our sun was born. But presolar grains raise their own questions. Scientists are still learning how to read them fully. The grains come in different types, from different kinds of stars, and sorting out exactly which stars contributed what is painstaking work. Each new meteorite studied adds a little more to the picture. The picture is still being drawn. Another open question involves timing. Scientists believe a massive star may have exploded in what is called a supernova, very close to the cloud that became our solar system. That explosion may have sent a shockwave through the cloud, helping to trigger its collapse and start the process of star formation. Some evidence for this comes from the ratios of certain elements found in meteorites. Elements that only form in supernova explosions, and that decay quickly over time. The ratios suggest they were added to our solar system's material very close to the moment of its formation, but the details are still debated. Exactly how close was that exploding star? Exactly how much did it contribute? Scientists are still working through the numbers. There is also the question of how common our situation is. Our solar system formed with a very specific mix of elements. That mix allowed rocky planets to form, allowed water to exist as a liquid, allowed chemistry complex enough to produce life. Evidence suggests that the mix of elements in a solar system depends partly on where in the galaxy that system forms, and partly on which nearby stars had already died and scattered their material. Some regions of the galaxy are richer in heavy elements than others. Some solar systems may have formed in clouds that were seeded more generously than ours. Some may have formed in clouds that were seeded less. Scientists are only beginning to map how this variation works across the galaxy and what it might mean for the chances of life forming elsewhere. Even the shape of our solar system may carry clues about its past. The way the planets are arranged, the tilt of their orbits, the composition of the outer planets, all of it reflects the conditions of the cloud from which everything formed. And that cloud was shaped, at least in part, by the deaths of stars that came before. Unraveling exactly how is a problem that planetary scientists, astronomers, and chemists are all working on together. What makes all of this so compelling is not the uncertainty itself, but what the uncertainty points toward. Every open question is a door. Behind each one is a more complete picture of how our solar system came to be and how tightly our existence is woven into the larger history of the galaxy. The atoms in your body passed through stars. The stars passed through time. The time stretches back further than the mind can easily hold. Scientists will keep asking. They will study more meteorites, observe more nebulae, build better instruments, and run more careful calculations. Slowly, the picture will sharpen, and each answer will almost certainly reveal a new question waiting just behind it. That is the nature of the universe. It is generous with its wonders and patient with those who look. Our sun is about 4.5 billion years old. That sounds ancient, but in the life of a star, it is roughly middle age. The sun has another 5 billion years or so of steady burning ahead of it. For now, it fuses hydrogen in its core, steady and reliable, the way it has always done. But that will not last forever. Slowly, over billions of years, the hydrogen in the sun's core will begin to run out. As it does, the core will shrink and grow hotter. The outer layers will respond by expanding outward. The sun will swell into what astronomers call a red giant, a star many times larger than it is today. Scientists estimate it will grow large enough to swallow Mercury and possibly Venus. Earth's fate is less certain. Some models suggest our planet will be consumed. Others suggest it will survive, though barely, and in a form nothing like what it is now. Long before that happens, the changes will be felt here. As the sun grows brighter over the next billion years or so, Earth's surface will warm. Oceans may begin to evaporate. The atmosphere will change. Life, as we know it, will face enormous pressure. 1 billion years is a very long time, and it is humbling to think that the same star that warms us today is already, slowly and quietly, moving toward a different chapter. After the red giant phase, the sun will do something remarkable. It will shed its outer layers into space. Those layers will drift outward in great shells and streams of glowing gas. The hot core left behind will shine with intense ultraviolet light, and that light will cause the surrounding gas to glow. Blues, greens, reds, and oranges will bloom across thousands of billions of miles. What we will have in roughly 5 billion years is a planetary nebula. Our sun will become the very thing this episode has been describing all along. The nebula the sun creates will not be the largest or the most dramatic. Because the sun has no companion star, its nebula will likely be relatively round and simple in shape. It may resemble something like the Helix Nebula, that wide, soft ring of glowing gas that sits about 650 light years from Earth. The helix is often called the Eye of God because of its circular shape and its glowing center. Our sun's nebula may look something like that. A quiet, glowing ring drifting slowly outward in the dark. That nebula will last for tens of thousands of years. During that time, it will scatter the sun's outer layers across a wide region of space. Those layers carry carbon, nitrogen, oxygen, and other elements built up over billions of years of fusion. They will mix into the surrounding gas clouds of the galaxy. In time, those clouds may collapse. New stars may form from them. New planets may gather around those stars. Some of those planets may carry, locked inside their rocks and oceans and atmospheres, atoms that once burned inside our sun. What remains at the center of all this will be a white dwarf, a dense, dim remnant size of Earth, but with a mass close to that of the Sun today. It will cool over billions of years, fading from white to yellow to orange to red. Eventually, far into the future, it may cool into a dark, cold object called a black dwarf. The universe is not yet old enough for any black dwarfs to exist, but the Sun's remnant will move in that direction, slowly, across timescales that stretch beyond easy imagining. There is something deeply settling about all of this. The Sun's death will not be violent or sudden. It will be slow and in its own way generous. The elements it spent billions of years building will return to the galaxy. They will become part of something new. The ending will carry the seeds of future beginnings, the way it always does out here. Planetary nebulae are not just beautiful objects in distant catalogs. They are previews. They show us, in glowing color, what our own star will one day become. Every time astronomers photograph one of these glowing rings or hourglass shapes or layered shells of light, they are looking at a version of our future, not a frightening one, a quiet one, a natural one. The Sun will live its full life, spend itself completely, and then release what it has made back into the universe. And the universe, patient and vast, will use every bit of it. Across the whole of the Milky Way, there are thought to be somewhere between 10,000 and 50,000 planetary nebulae glowing right now. That number sounds large, but our galaxy holds somewhere around 200 billion stars. When you set those two numbers side by side, you begin to feel just how rare and brief these glowing clouds truly are. They are fleeting moments in a very long story. Most of them are invisible to the naked eye. They are too faint, too far, or too small in the sky to see without a telescope. But they are out there in every direction, scattered across the flat disk of the galaxy like embers cooling in the dark. Some drift near the crowded center of the Milky Way, where stars are packed tightly together. Others float in the quieter outer edges, where stars are spread far apart and space feels emptier and still. The ones near the galactic center are harder to study. Thick clouds of gas and dust fill that region of the galaxy, blocking the light that tries to pass through. Astronomers use infrared light, which can pass pass through dust the way a radio signal passes through a wall to find the nebulae hiding behind those clouds. Every time they do, they find something new. The center of the galaxy is full of history, and planetary nebulae are part of it. The ones in the outer galaxy tell a different story. Stars in those regions tend to be older and contain fewer heavy elements than stars born closer to the center. That means the nebulae they produce are slightly different in their chemistry. They still glow. They still scatter carbon and nitrogen and oxygen into space. But the exact mix of what they release reflects the environment where their parent star was born. Sometimes billions of years ago, a planetary nebula carries the memory of its star's whole life inside its glowing shell. When astronomers map all of these nebulae across the galaxy, a pattern begins to emerge. They are not spread out evenly. They cluster along the spiral arms of the Milky Way, the long curving bands of stars and gas that give our galaxy its shape. This makes sense. The spiral arms are where star formation is most active, where gas clouds collapse into new stars, where the cycle runs fastest. Planetary nebulae trace that activity the way footprints trace a path. Our solar system sits inside one of those spiral arms, about halfway between the galactic center and the outer edge. We are not in an unusual place. We are not in a special location. We are simply one small system among hundreds of billions in a galaxy that has been running this same cycle for over 10 billion years. Stars are born, they live, they shed their outer layers, and those layers feed the next generation. It has been happening long before our sun existed, and it will keep happening long after. Scientists estimate that the Milky Way produces several new planetary nebulae every year. Each one represents a star reaching the end of its life. Each one releases a cloud of enriched material back into the galaxy. Over time, that material mixes with the surrounding gas. It cools. It drifts. Eventually, gravity pulls it together again, and a new star begins to form. The cycle is not a metaphor. It is a physical process, measurable and real, playing out continuously across the galaxy right now. The oxygen you breathe passed through at least one star before it reached you. carbon in every living cell on Earth was forged inside a stellar core and scattered outward when that star died. Some of that carbon may have traveled inside a planetary nebula, glowing briefly in the dark before cooling and drifting, and eventually becoming part of a new solar system, part of a planet, part of you. That is not a small thought. It is the largest thought there is. You are not separate from the universe. You are made of it, shaped by it, returned to it in the end. The atoms in your body have been through stellar fires. They have floated in glowing clouds. They have drifted through cold space for millions of years before finding their way here. Planetary nebulae are not just beautiful objects in distant corners of the galaxy. They are part of the process that made everything. Every ring of glowing gas, every hourglass of expelled light, every layered shell drifting outward from a dying star is a moment in a cycle that has no clear beginning and no clear end. The galaxy breathes these things out and breathes them back in. Slowly, steadily, with a patience that makes all of human history feel like a single quiet breath. And so we arrive here at the end of this long and quiet night of wonders. We have traveled through the lives of stars. We have watched them swell and brighten, and slowly let go of everything they carried. We have seen their outer layers drift outward in rings and hourglasses and butterfly wings of glowing gas. We have watched white dwarfs shine at the center of all that color, pouring out ultraviolet light, painting the clouds around them in shades of red and blue and green. We have seen how those clouds cool and thin and fade, and how the atoms inside them drift on through the dark until they find new homes. It is a long story. It is a patient one. And here is one last gentle thought to carry with you into sleep. The universe is very old. Scientists estimate it is about 13.8 billion years old. Our own galaxy, the Milky Way, has been forming stars for nearly that entire span of time. Somewhere in this galaxy, right now, a star is reaching the end of its long life. It is swelling. It is brightening. It is beginning the slow, graceful process of letting go. And the gas it sheds will glow for tens of thousands of years before it fades into the background of space. That glow is happening right now in dozens dozens of places across the sky, even as you rest here in the dark. There are thought to be around 10,000 planetary nebulae in the Milky Way alone. Most of them we cannot see with the naked eye. They are too far, too faint, too small against the vast field of stars. But they are there, quiet rings of light, slowly expanding, slowly cooling, carrying their cargo of carbon and nitrogen and oxygen outward into space. Each one is a small act of generosity from a dying star. Our own sun will do this one day. In about 5 billion years, it will swell into a red giant, expand past the orbit of Mercury and Venus, and eventually shed its outer layers in a slow, glowing cloud. What remains will be a white dwarf, roughly the size of Earth, slowly cooling over billions of years. The nebula it leaves behind will glow for a time, and then fade, and the atoms it scattered will drift on. Some of them may find their way into a new solar system. Some may become part of a new planet. Some may, in ways we cannot predict or imagine, become part of something alive. That is not a frightening thought. It is a peaceful one. The sun has already given us everything. It has warmed this planet for 4.5 billion years. It has driven the winds and the rains and the slow growth of forests. It has made photosynthesis possible, and through that, all animal life, including us. When its time comes, it will give one final gift. It will return to the galaxy what the galaxy once gave to it. Right now, outside, the night is doing what it always does. The Earth is turning slowly on its axis, the way it has for billions of years. The oceans are resting under starlight. The forests are quiet. The atmosphere, that thin and fragile shell of air, holds everything gently in place. Above it, the stars are there, the same stars that ancient people watched, the same stars that will be there long after us. And somewhere among them, faint and distant, a planetary nebula is glowing. A ring of gas is drifting outward. An old star is cooling at the center of it all, still shining, still giving off light, still doing its quiet work. You are part of this, not in a vague or poetic way, in a real, physical, chemical way. The atoms in your body were made in stars. They have been through heat and pressure and cold and darkness and light. They have traveled enormous distances across enormous spans of time to be here, in this moment, in this body, breathing slowly in the dark. The universe is not indifferent to you. It made you. It carried you here across billions of years of stellar fire and drifting gas and slow, patient gravity. And tonight, as you drift toward sleep, the galaxy is still turning. The stars are still burning. The nebulae are still glowing softly in the dark between the stars. Everything is continuing. Everything is connected. Everything is at rest and in motion at the same time. And so are you. Sleep well. Subscribe for a brand new space topic every night. One tap and something incredible is waiting for you tomorrow. Sweet dreams.